All right, today we're going to cover something called the empirical formula. So, the word empirical means experimentally determined. Okay, experimentally determined. Sometimes in the legal sense, it means that it's based on fact, right, like evidence. Okay, and that is true here in lab. You're going to see that it is based on numbers that we collect. What it also means is that it means that the subscripts are going to be in the lowest whole number ratio, right? Another way of thinking of it is it's the simplest or reduced formula. Okay? You know, like instead of 4 and 2, it would be 2 and 1. Right? Instead of 6 and 2, it would be 3 and 1. Okay? So, when we look at a formula for a compound like hydrogen peroxide is H2O2, but that is not the simplest ratio. The simplest ratio is HO. Right? So therefore, HO is what we call the empirical formula. The H2O2 is actually what we call the molecular formula. So molecular formula is, think of it as the real formula. The real formula. Okay, whereas empirical, again, means simplest. There are times when you need to know one or the other, right? And we need to learn them in order. So we're going to learn the empirical formula first. So this is how we find the empirical formula. Let's do it learn it by doing an example. So let's say that we have some unknown compound, and compound has a mass of 2.571 grams. Right? So that's our sample. This compound contains 1.102 grams of carbon, 1.469 grams of oxygen. So it's made up of two elements. And they want to know what the empirical formula is. So the first thing you need to do is you need to convert to moles. And you're going to do this by using the molar mass. So I'll rewrite it in dimensional format, dimensional analysis format like you're used to seeing. So what we do is we take 1.102 grams of carbon. The molar mass of carbon is 12.01. Right? So by dividing, we get 0.09176 moles of carbon. And I know this answer right here. I know this shows the same thing, but I'm going to urge you and suggest to you that whenever you do mole conversions, use the bracket method setup, right? Because it will be much easier to track your units. And when you can track your units, you can have an easier time seeing if you set things up correctly or not, right? So here I can clearly see that my grams and my grams have to cancel. Okay, let's do the other one. So 1.469 grams of oxygen. A mole of oxygen is 16.00 grams. So the calculation gives me 0.09181 moles of oxygen. My units cancel like so. All right, and so now what I have is I have the moles of both elements. That is step one. Convert to moles. So the next thing I do is I have to figure out a ratio between these two elements, and the only way you can find a ratio between elements is if it's a mole ratio. So that means I pick the number of moles which is smaller between these two. This one is smaller. And what I'm going to do is I'm going to divide both of these numbers by this one. So, and that's shown here, right? So 0.09181 moles of oxygen divided by 0.09176 moles of carbon. And that number turns out to be essentially 1.001. And the carbon, of course, the number of moles of carbon divided by itself is going to be 1. So essentially what I have here is I have two numbers that are the same. They're both 1. And that's totally fine because that can happen. All right, we're starting easy here. We'll see other ratios here in just a second. So what that tells me then, for every 1 carbon, there is 1 oxygen. And so my formula is going to be CO. And remember, we don't write subscripts of 1. I mean, you can, but it's just not convention to do that. As far as which element comes first in your compound, generally it's the lower electronegativity which comes first, or farthest to the left on the periodic table it comes first. Okay. So really there's 2 steps. Convert what you have into moles and then divide them to get some kind of ratio or some kind of integer. Like here, the integers we got were 1 and 1, and then we combine them to form a formula. Let's try another one. All right, so 2.338 grams of a compound contains 0.7117 grams of nitrogen, and the rest is oxygen. Okay, so they're telling me the rest is oxygen, but they didn't tell me what the number was. So my first step is I got to figure out how much of the other one there is. Right, so 2.338 grams total minus 0.7117 grams of nitrogen. And since there's only 2 elements mentioned, that means the difference must be the grams of oxygen. So let's find that out. Okay, so 1.6263 grams of oxygen. All right, I have my mass of both elements now. So convert to moles. 0.7117 grams of nitrogen. A mole of nitrogen is 14.01 grams. .05080. Okay, and now that we know the oxygen, 1.6263 grams of oxygen. A mole of oxygen is 16.00. .1016 moles of oxygen. Okay, there's my moles of both. The second step is to divide both of these by whichever number of moles is smaller. Question, Chris?
Where 14 come from? 14.0.
Oh, that's the molar mass of nitrogen from the periodic table.
Oh,
Okay, so which number am I going to divide both of these by? The smaller, right? 0.0508. Any number divided by itself, of course, is 1. And this ends up being 2. So my formula will be NO2. That is my empirical formula. Make sense? Find moles. Divide both moles by whichever is smaller. Now, you could have 3 elements in a compound. You could have 4. The number of elements in a compound doesn't matter. Just whichever one is the smallest number of moles is the one you divide everything by. And when you do, you should have integers that you can work with. Okay? Let's try one more. Now, this time, instead of being given grams, you might be given percentages. Right? So if you are given percentages, then you are just going to turn each percentage into grams, meaning you're assuming a sample size of 100 grams. Now, the reason why we would do this, like if I said I had 100 grams of a compound, right, and then here in this problem, they're telling me that there's 32.37 grams of sodium. Well, if I have 100 grams, that means I really do have 32.37 grams. of sodium. So the total amount of the substance is relative, right? Just go ahead and assume a sample size of 100 grams, and therefore you can use these percentages like they are grams. So I'm going to carry out the same procedure that I just did, but I'm going to use the percents as grams. So I start with that many grams of sodium. (23 grams per mole). All right, so this is 1.407 moles of sodium. Okay, let's do the next one. 22.57 grams of sulfur. A mole of sulfur weighs 32.07 grams. .7038. And 45.06 grams of oxygen. All right. Finish the problem and tell me what you get. And at the end of the day, hopefully you end up with a formula that makes sense based on what you know about formulas and charges. What do we think? Who's got it? Nishka, what'd you get?
Na2SO4.
Good. That's right. So let's walk through this. We have the moles of everything. So we pick this number because this is the smallest. So that number divided by itself, of course, is 1. And then the 1.407 divided by the smallest number will give us 2. And then the 2.8 divided by that number will give us 4. And so we piece together the formula. Sodium has the lowest electronegativity, put that first. Oxygen has the highest electronegativity, put that last. And that's our formula. That's how you find an empirical formula. So you can find it from either grams or percents. Okay? And on your homework, questions 1 through 6, that's what these problems are going to be like. It's you figuring out the empirical formula.